Hello, today we're going to be looking at AP Review 13, Riemann sums and more. Problem number 1, a test plane flies in a straight line with a positive velocity, miles per minute. Miles per minute, okay. Selected values from 0 to 40 minutes is in the table. Those are velocities, okay. Use a midpoint Riemann sum with 4 subintervals of equal length. So 40 minus 0 over 4 equals 10. So I want to go 0 to 10 is my first interval. I go halfway across that interval and use that height. So the integral of v of t from 0 to 40 is approximately the subinterval width, 10, and that's going to be the same for each of these, so I'm just going to add up 9.2 plus the next interval goes from 10 to 20, halfway across is 15, I use that height, plus the next interval goes from 20 to 30, I go halfway across that interval and get that height. And then finally, the last rectangle goes from 30 to 40. I go halfway across that interval and I pick up the height there, 4.3. My recommendation is that you leave your answer like this. But if you need to, if you have that inner drive and need, that's 229 miles that we just figured out. Because we've got here, these are minutes, and these are miles per minute, and minutes cancel even, leaving us with miles. Okay, so let's see. Use a midpoint Riemann sum to approximate that. I did that part. Show the computations. Use correct units to explain the meaning in terms. Oh, okay. So the plane flew. None of these are negative, so I assume that, does it say differentiable function, selected values? Yeah, I'm just going to go with flew 229 miles during the first 40 minutes of the trip. Okay, that's A. B. B says, based on the values in the table, what's the smallest number of incidents when acceleration could be equal to 0 on the open interval? Okay, so we know that acceleration equals v prime. And so we're talking about the slopes of v here. We're talking about the v increasing to decreasing, or v going from decreasing to increasing. At these moments, v is going to have a max, a min, well, I guess you could just have a horizontal tangent, but v prime will be equal to 0. V prime isn't going to be undefined because v is a differentiable function, and so v exists, the derivative of v exists everywhere. So I'm going to be finding, when I see this, therefore v equals 0, v prime equals 0 at those places. So let's see what we've got here. We seem to be increasing, but now we're going decreasing, and then we're still decreasing, and then we're increasing again, and so I would say twice. At least twice v prime equals 0. because of that. I guess you could also use Rolle's theorem here, but we didn't talk about Rolle's theorem, and we didn't do student presentations that would discuss Rolle's theorem, so that's what we're going with. Okay, part C. Function f defined by this interesting thing is used to model the velocity of the plane. Okay. On 0 to 40, according to this model, what is the acceleration of the plane at 23? So I want v prime equals a, and I want v prime equals a of 23. And this is with calculator, so I'm just going to pull out a calculator and type this in. Don't forget to be in radians. I get negative 0.408 miles per minute per minute. And do they ask me to explain what that means? No, but find it and indicate units of measure. I've got that. Can I get D in here? According to the model in part C, what is the average velocity of the plane on 0 to 40? Well, they gave me a velocity function, and they want the average velocity, so they want the average value of the given function. So we want 1 over 40 minus 0, integral 0 to 40 of f of t dt, and that's going to be, when we do that in our calculator, 5.916 miles per minute. So if we were to consider the average of all the different velocities from 0 to 40, the average of all those different velocities given our f function will be this many miles per minute. Okay, that's problem number 1. How about problem number 2? Problem number 2 says, find the average acceleration. Average acceleration. So if I want average acceleration, I want 1 over 80 minus 0, the integral of a of t dt. Now, a of t is the same as v prime. And remember, according to FTC2, this would be v of 80 minus v of 0 over 80 minus 0. So what do we have then? We've got velocity, sorry, wrong table. Velocity at 80 is 49 minus 5 over 80, which is 44 over 80. You could certainly reduce that or decimalize it as 0.55 feet per second on top. That's velocity units on top. And on the bottom, we have seconds. So feet per second, or feet per second squared. Okay, so that's 2. A, indicate units of measure. Yes, I did. B. B says, using correct units, explain the meaning of the integral from 10 to 70 v of t dt in terms of the rocket's flight is how far the rocket traveled in feet from the 10th to 70th second of its flight. And then we're supposed to use a midpoint Riemann sum with 3 subintervals of equal length to approximate that number of feet. Okay. I guess instead of how far the rocket traveled, I could also say net change in position on from 10 seconds to 70 seconds. Okay, and now we're supposed to approximate this by using a midpoint Riemann sum with 3 subintervals. So my delta x equals 70 minus 10 over 3 subintervals. Get 60 over 3, or 20. So my subinterval width is 20. If I look here, I'm going from 0 to 20. I'm going to use the time value in the middle of that interval and a height of 14. So my subinterval widths will all be 20. I'm using a height of 14. The next interval, no, it isn't, Mr. Kukla. We're not starting at 0. We're starting 10 to 30. The middle is 20. So I need 22. Okay, and then the next subinterval goes from 30 to 50. Halfway across is 40. I use that height of 35. And then from 50 to 70, halfway across is 60. And I have a height of 34. Okay, so that's going to be the distance. That's 60, 90, 99, 101, 20 times 101. And I get 2,020 feet traveled. Okay, there's part B. Part C says the rocket launches upward with this acceleration, 3 over square root t plus 1. At time equal to 0, the initial height is 0, and the initial velocity, v of 0 equals 2, and x of 0 equals 0. So what am I supposed to do? I'm supposed to figure out which is traveling faster at 80. Okay, so I want v of 80 for rocket A and v of 80 for rocket B. Well, v of 80 for rocket A is 49 feet per second. So let's find v of 80 for rocket B. Now, this is acceleration, which is also known as v prime. And if I integrate v prime, I'm going to end up with v plus c. So, in fact, I could think about this even better. V 80, 0, v of 80 minus v of 0. So v of 80 will be the integral from 0 to 80 of v prime dt plus 2. Okay, and when I integrate that, I get, I don't have a value here for you. Oh, yes, I do. 80. This is without calculator. Okay, so I've got to do some computation. All right, let's do some computation. I want to integrate 3 square root of t plus 1 dt, u equals t plus 1, du equals dt, and so then I'm integrating 3 integral u to the minus 1/2 du. The antiderivative there would be u to the 1/2. If I brought down the 1/2, I don't see a 1/2. There must be a 2 here times the 3. And I want to evaluate this from 0 to 80, t plus 1, so that's 81, and 0 plus 1 is 1. So I have the square root of 81, which is 9. 9 times 6 is 54, minus, I plug in a 1, the square root of 1 is 1, times 6 is 6, and so that gives me 48. So, don't forget though, that's the value of the integral. So we have 48 plus 2, or 50, is v sub b of 80. So rocket B is traveling faster at t equals 80. Okay. Number 3. 3 is without calculator. It looks like until we get to the last problem, all of these are without calculator. Okay. Next one, we've got a spherical balloon expanding. Twice differentiable function r of t, where t is measured in minutes, 0 to 12. Graph of r is concave down. R is concave down. Okay. And I know that because r prime in the table is decreasing, but they're telling me, look, even in the spaces in between the points we've given you, you're going to see that r prime is always decreasing. Okay, that's nice to know. Part A, estimate the radius of the balloon when t equals 5.4. So I would think about using a tangent line approximation at t equals 5. So at t equals 5, the radius is 30. And so we've got 5 comma 30. And we want r prime at 5. And that is 2. And so then my tangent line, y minus 30, equals 2t minus 5. And we want to approximate y minus equals 5.4 minus 5 plus 30. That's going to be 0.4 times 2 is 0.8, and I get 30.8. 30.8 for 3A. Yes, now, does it go even further? Is this greater or less than the actual value? Well, we're building a tangent line to R. R prime is always positive. R double prime is always negative. So R is, didn't they tell me? R is concave down. Well, since R is concave down, whether I'm looking at that or whether I'm looking at that, my tangent line approximation is an overestimate, since R is concave down always. Okay, there's a bunch of stuff for part A. How about part B? Part B says find the rate of change in volume. Rate of change in volume with respect to time. We want dv dt at t equals 5. Indicate units of measure. All right. So we know v equals 4/3 pi r cubed. And so v prime, or better, let's use appropriate notation, dv dt equals 4 pi r squared. Don't forget to take the derivative of that inside r function with respect to time. Now dr dt is our r prime from the table. So dr dt at 5 is 2, so this value is going to be 2. But what about the radius? We want r, the radius, at 5. So the radius at 5, the radius at 5 is 30. Okay, so then dv dt equals 4 pi 30 squared times dr dt, which is 2. And I end up with 900 times 8, 7,200 pi, and the units, because it's a change in volume, are going to be cubic feet per minute. Cubic feet per minute. Okay, you could certainly leave it with this expression as long as you had cubic feet per minute there, because they did want to know the correct, they wanted us to indicate units of measure. So here's B. C, use a right Riemann sum with 5 subintervals, and the subinterval widths are different everywhere, to approximate the integral from 0 to 12 of r prime. Okay, so 3C. We're doing a right Riemann sum, so we want not to use the first height, but to use the second height and all the heights after that. So the first rectangle, 2 minus 0, is the base, and the height is 4.0. And the second rectangle is 5 minus 2, and the height is 2.0. And the third rectangle is 7 minus 5, and the height is 1.2. And the fourth rectangle is 11 minus 7 times the height of 0.6. And finally, we have 12 minus 11 times a height of 0.5. That's going to be, that's our approximation of 0 to 12 of r prime dt, is that approximately. Now remember, this is equal to r of 12 minus r of 0, which is the change in radius from t equals 0 to t equals 12. Okay. Use correct units, explain the meaning of that. Oh, well, we did that. This turns out, by the way, if you actually wanted to waste the time to figure it out, to be 193 feet. Okay, and these are, don't forget, minutes. That's 3C. What about 3D? Is your approximation in part C greater than or less than? So we did a right Riemann sum, and we did a right Riemann sum since r is concave down. R prime is decreasing on 0 to 12. And if r prime is decreasing, and we do an underestimate, we do a right Riemann sum. Let's take a look at these. Our right Riemann sums. Right Riemann sums, since r prime is decreasing, a right Riemann sum would be an under estimate. Okay, there's 3D. Let's take a look at problem 4. 4 says velocity of particle moving is given by this differential part of this. No, velocity is modeled by a differential function v, where the position is measured in meters and time is in seconds. We know position is 0, is 7, and these are meters and seconds. Okay. Estimate acceleration at 36. So A of 36 is V prime of 36, which is approximately, that's instantaneous rate of change. I can use average rate of change, V of 40 minus V of 32 over 40 minus 32. We can't stop here. We have to actually take the values from the table and plug them in. Minus a minus 4 over 8, and I get 11 over 8. And the units are going to be, the units here are meters per second, and the units here are seconds. And so I get 11 over 8 meters per second per second. Okay, B. B says, using correct units, explain the meaning of the integral from 20 to 40 of v t dt. And if I integrate this, that would be x of 40 minus x of 20. And we know this is the net change in position. It's not the total distance traveled. Note, we've got some velocities that are negative here, so we know this object is traveling back and forth, and as a result we're just going to find a change in position here. So use a trapezoid sum with 3 subintervals to approximate the value. Okay, so trapezoid, 3 subintervals from 20 to 40. The subinterval widths are different, so I have to write the approximation as separate. Dt is approximately 1/2. The first one goes 25 with 20 to 25, and the heights are -10 plus -8. The next one goes 25 to 32, so 32 minus 25. And the heights there are -8 plus -4. And finally, the last one is from 32 to 40, so 40 minus 32 times -4 plus 7. Okay, and let's put a this here and a this here. This is without calculator, so I wouldn't waste the time computing all of these. You do end up with -75 meters, or the object, the particle is 75 meters to the left of where it was at t equals 20, and I believe these are seconds. Okay, great. So now part C says, for 0 to 40, must the particle change direction in any subinterval indicated by the data? Sure. Velocity was positive, then velocity is negative, then velocity is positive again. Because v changes from positive to negative and then negative to positive, v must equal 0 at least twice since, do we have to justify this? As indicated, if so, explain the identify the subintervals. Okay, and explain your reasoning. Okay, so changes from positive to negative on somewhere between 8 and 20, and then goes from negative to positive on 32 to 40. So v equals 0 at least twice, since v is continuous. IVT says v must pass through all values as it goes from negative to positive and from positive to negative, must pass through zero as, don't say it, as velocity. Goes from negative to positive or positive to negative. Okay, you don't have to use IVT here. I just found it useful to use IVT here. Okay, that was for C. For D, suppose the acceleration of the particle is positive for 0 to 8. Okay, acceleration is positive, which means that v is increasing everywhere. Okay, that makes sense. Which means that position function would be concave up. All right. Explain why position must be greater than 30. Why the position must be greater than 30. I wasn't expecting that question. Let me think about that. Position must be greater than 30. Well, let's think about x of 8 minus x of 0 equals the integral from 0 to 8 of v of t dt. 0 to 8. So, didn't we know position at 0 to be 7? So x of 8 equals 7 plus 1/2. I'm just going to do a little approximation here. 8 minus 0, 3 plus 5. And so I get 8 times 8 is 64. Divided by 2 is 32, plus 7 is 39. So, and this is a trapezoid sum approximation. Was I using, which sum did we used a trap sum here, so I feel good about using a trap sum since x of 8 using trap sum is 39. And remember, we've got this function v. It's an increasing function. So let's look at some increasing functions. And let's consider a trapezoid sum with these increasing functions. Notice, oh, not in this case. So in the concave up case, my trapezoid sum would be an overestimate. But in a concave down case, my trapezoid sum would be an overestimate. Acceleration is positive. Ah! That means this one. I don't like that. Okay, so let's see. You know what? I don't want to use trapezoid sum. I've got some other sums. Let's use some other sums. Let's use LRAM here, and if I do LRAM, I'm going to have 8 minus 0 times 3, or 24. Don't forget to add that 7, so x of 8 equals 7 plus 24, or 31. And RRAM is 8 minus 0 times the height over there, which is 5, and I get 40. So x of 8 equals 7 plus 40, or 47. So I see that the value, suppose acceleration is positive, and position must be greater than 30. So since the smaller approximation with LRAM is 31, and that is greater than 30, we know which must be greater than 30, yes, and that is greater than 30. Smiley face, that's what I was looking for. All right, so that was for D. For D5. Okay. Particle moves along the x-axis with position at time t given by x of t equals e to the minus t sine t on 0 to 2 pi. And this is position, not velocity. Find the time when the particle is furthest to the left. Find the time when the particle is furthest to the left. So let's take a look at velocity. V of t equals, that's a product, so I need product rule. Negative e to the negative t sine t plus e to the negative t times cosine t. If I factor out an e to the negative t, I get cosine t minus sine t. Now, when is v equal to 0? Well, this is never equal to 0. This is equal to 0 when cosine equals sine, and that happens at t equals pi over 4 and 5 pi over 4. So I've got some critical values for 0 to 2 pi. They are pi over 4 and 5 pi over 4, and this is v. So if I plug in a 0 to v, cosine of 0 is 1, sine of 0 is 0, e to the 0 is 1, I get positive. If I plug in a number on this interval like pi, cosine of pi is negative 1, sine of pi is 0, e to the pi is some positive thing, positive times negative 1 is negative. And if I put in 2 pi over here, cosine of 2 pi is 1 again, minus 0, I still have a positive times a positive, so I have a positive. Okay, so I'm changing directions twice here. And my question was, when is this object furthest to the left? Okay, so I've got a velocity function like this, and I don't know what it looks like. So I start at some point, and I travel to the right. I stop, I travel to the left. I stop, I travel to the right. So I think I actually want to use a candidate's test here and find position at each of these different locations. They did give me an initial position. No, they did not give me an initial position. So x of 0 is 0. Okay. So let's find our positions at these different places. X of 0 equals 0. X of 2 pi equals e to the minus 2 pi times sine of 2 pi. Well, the sine of 2 pi is 0, and so I'm back at 0 again. Okay, and then we also had x of pi over 4, which would be e to the negative pi over 4, and then sine of pi over 4, which is root 2 over 2, times 1 over e to the pi over 4. And then I need x of 5 pi over 4, which is e to the minus 5 pi over 4. Sine of 5 pi over 4 is negative root 2 over 2 times 1 over e to the 5 pi over 4. Okay, so furthest to the left is most negative. Both of these are positive. This is 0. This is positive. This is the only negative one, so I'm furthest to the left at t equals 5 pi over 4 according to the candidate's test. Okay, and I justified my answer. Okay, part B. Part B says find the value of the constant a, which satisfies the equation a x double prime plus x prime plus x equals 0. So x, remember, was e to the minus t sine t. X prime was, and we already computed x prime, didn't we? We said that was velocity, and that was e to the negative t cosine t minus sine t. And so x double prime is going to be another product rule. This derivative times all this stuff plus this e to the minus t times the derivative of this, which is minus sine, times the derivative of this, which is minus cosine. Okay. And now we've got an a in front of all of this. So let's see what we can build. A times, I'm going to distribute and see if there's any like terms to combine. Negative e to the negative t cosine t plus e to the negative t sine t plus e to the negative t, negative sign, so that's minus sine t plus e to the negative t cosine t. All of that times a. Plus e to the negative t cosine, I'm just going with the big old distributing thing, minus e to the negative t sine t, and then I want to add x, e to the negative t sine t. And I want that sum all to equal 0. Okay, so what do I see here? Well, I see that these cancel each other out. And I see that these cancel each other out. Why does it look like these are going to cancel each other out? So I've got a mistake somewhere and I've got to try it again. Okay, that's great. Let's go again. So we started off with e to the minus t sine t, and our first derivative was e to the minus t cosine t minus sine t, and our second derivative was e to the minus t negative e to the minus t cosine t minus sine t plus e to the minus t negative sine t minus cosine t. Okay, if I distribute the negative, let's just push the negative in. Okay, now I can factor out the e to the minus t, shove an a there, and I've got negative cosine t plus sine t minus sine t minus cosine t. I think that's where my sign mistake was. And then I have an e to the minus t cosine t minus sine t, and then an e to the minus t sine t. Okay, I'm going to factor out the e to the minus t, and I'm going to combine these like terms, and I'm going to see that e to the minus t times a, and then we've got minus 2 cosine t plus cosine t minus sine t plus sine t equals 0. Well, this never equals 0, so I'm just going to be setting this equal to 0. Okay, and combine like terms, these go away, and I get negative a cosine t equals 0. Oh wait, this one had a 2a. This a doesn't go to everything. Damn. So I've got negative 2a cosine t plus cosine t equals 0. Or cosine t equals 2a cosine t. If I divide by cosine t, I get 2a equals 1, or a equals 1/2. Be patient. You'll get there. That's my words for today. Okay, 5, 6. Let's take a look at problem number 6. 6 says f is a function that's twice differentiable. We've got values of f on the closed interval from 2 to 13. This is problem number 6. Okay, estimate f prime of 4. Show the work that leads to your... Well, we can approximate the slope at a point by using the average rate of change, f of 5 minus f of 3 over 5 minus 3. And so that's going to be negative 2 minus 4 over 5 minus 3, which is negative 6 over 2, or negative 3. So f prime of 4 is approximately negative 3. Great. Part A done. Part B. Evaluate the integral from 2 to 13 of 3 minus 5f prime dx. Well, with my integral properties, that's 2 to 13 of 3 minus 5 times the integral of f prime from 2 to 13. This is just going to be 13 minus 2 times 3, or 33, minus 5 times. Now this is going to be f of 13 minus f of 2. F of 13, according to the table, is 6. F of 2 is 1. So I get 5 times 5, or 25. 33 minus 25, or 8. Do we have to say anything about units of measure? No, just indicate your work. There's my work. We move on to part C. 6C. 6C says, use a left Riemann sum with the subintervals indicated by the data, and I noticed that those subintervals don't have a consistent width, so I'm going to have to do separate rectangles for each. 2 to 13 of f of x dx is approximately 3 minus 2 times left Riemann sum, so we use that first value, plus 5 minus 3 times 4, plus 8 minus 5 times negative 2, plus 13 minus 8 times 3. It's sufficient to leave your answer like this, but if you want to tidy this up, you should end up with 18. Okay. Show the work that leads to your answer. Done. 6D. 6D says, suppose f prime of 5 is really 3, and f double prime is less than 0, so that means f is concave down always. Okay, on the closed interval from 5 to 8, 5 to 8. Alright, use a tangent line, the graph at 5. Okay, so I have a slope at 5, and I need an ordered pair. 5, my f of 5 equals negative 2. And so y minus a minus 2 equals 3x minus 5. And I get y equals 3x minus 15 minus 2 is minus 17. Okay, so, and what do they want me to do here? Show that f of 7, use a tangent line to show that f of 7 is less than or equal to 4. Use a secant line. Oh, well, we're just using the tangent line. So our tangent line approximation for f of 7, y of 7 equals 21 minus 17 equals 4. Okay, so I know that this function is concave down and increasing, concave down, and what interval are we on? 5 to 8? 5 to 8. Did I do 8 to 13 by mistake? Let's check. F prime, f of 5 is negative 2. No, okay. So from 5 to 8, f is increasing and concave down. So I've got increasing and concave down. And so the tangent line approximation, since f is concave down, tangent line is an overestimate. So f of 7 is less than or equal to 4. Okay, but now wait, there's more. Now we've got the secant line to talk about. So the secant line from 5 to 8, the secant line is this line. And that is the line between those 2 points, and those 2 points are 5, negative 2, and 8, 3. So I need a slope, 3 minus a minus 2 over 8 minus 5. I get 5 over 3. 5 over 3 is my slope. Okay, and I've got an ordered pair to work with, so y minus 3 equals 5/3 x minus 8. And we want to know about 7. Okay, so 7, If I plug a 7 in there, y equals 3 plus 5/3, 7 minus 8. That's 9/3 minus is 4/3. Okay, so this time I get 4/3, and I want to say, hey, look, the secant line is an underestimate for my increasing concave down f. Therefore, f of 7 has to actually be bigger than 4/3. Okay, whole bunch of work in 6D, but not so hard, just a whole bunch of work. Problem number 7. 7 says we've got a twice differentiable function f. We're told that f of 0 equals 2, f prime of 0 equals -4, f double prime of 0 equals 3. Oh, the mischief we'll get into with that knowledge. Okay, so what do we know? G, a completely different function, is given by e to the ax plus f of x. Okay, for all real numbers where a is a constant, find g prime of 0 and g double prime of 0 in terms of a. Show the work. Okay, so let's first find g prime of x. G prime of x is going to be a e to the ax plus f prime of x. And so g prime of 0 is going to be a times e to the 0 plus f prime of 0, which is a minus 4. I get a minus 4 for my first value. And then what about g double prime? Well, g double prime is going to be a squared e to the ax plus f double prime of x. So then a double prime of 0 equals a squared e to the 0 plus f double prime at 0, which is a squared plus 3. I get a squared plus 3 for g double prime at 0. All right, 7a done. 7b. I sure could get used to these problems that have only 2 parts. But that one was so quick, I'm worried how long this one will take. The function h, oh, yet another function. H equals cosine kx times f of x. And here they want me to find h prime of x equals, write an equation for the line tangent to this. Okay, so h prime of x requires a product rule, and so the derivative of this is going to be minus sine kx times k times that, plus that cosine kx times the derivative of that f prime of x. And we're asked to write the equation of the tangent line at 0, so I need h of 0, which is cosine of 0 times f of 0. Cosine of 0 is 1. F of 0 is 2. So 1 times 2 is 2. So I have the ordered pair 0, 2. Now I need h prime at 0, which is going to be minus sine of 0 times k times f of 0. But since the sine of 0 is 0, all this goes away. Cosine of 0 is 1 times f prime of 0. And f prime of 0 was -4. So h prime of 0 equals -4. So I think I've got this, here's my ordered pair, here's my slope at that point. I think I'm ready to write the equation of the tangent line. So y minus 2 equals -4x minus 0. or y equals negative 4x plus 2. Either one of these is fine for 7b. And that felt pretty easy and straightforward. Was that okay for you? I mean, wow. And it was only 2 parts. Let's go. Number 8. Yeah, too bad that was 2006. The further away from today's date it is, the less likely it will be to be that kind of a problem on the AP exam. I contend the AP questions have gotten harder in the last 30 years. But maybe they're just different. Problem number 8, our last problem. This one is again with calculator. This one says, explain why there must be a value. Ooh, and we've got h of x defined in this interesting way. F of g of x minus 6. I'm sure many students will forget that minus 6, but let's go along and see what it says. Explain why there must be a value r such that h of r equals negative 5. H of r on 1 to 3. Okay, so since h is continuous because f and g are continuous, IVT says h must pass through all values from h of 1, which is f of g of 1 minus 6. G of 1 is 2, f of 2 is 9, 9 minus 6 equals 3, to h of 3, which is f of g of 3 minus 6. G of 3 is 4, f of 4 is negative 1, negative 1 minus 6 is negative 7. So IVT says we must pass through all these values, which includes the value negative 5. This is the IVT question, part A. I'm guessing that part B is the MVT question. What do you think? So here they then say h prime at some point must equal negative 5. So again, I suspect this is going to be h of 3 minus h of 1 over 3 minus 1. That's what MVT says. But remember, in these problems these days, it wouldn't be sufficient just to start with MVT. We need to address the preconditions, and so we have to say that h is continuous on continuous and differentiable on 1 to 3 because f and g are differentiable. Okay, so that being said, then therefore, according to MVT, there must be a point x equals c such that h prime of c equals h of 3 minus h of 1 over 3 minus 1. Okay, so h of 3 was negative 7. H of 1 was 3 over 3 minus 1 is 2. Negative 10 over 2 equals negative 5. Therefore, h prime of c must equal negative 5 on 1 to 3. Done. Okay, that was part B for number 8. What about part C? C says, let W be defined in this interesting way. Integral from 1 to G of f of t dt. Okay, and we want to know W prime. So here's an opportunity for us to use G of x. Here's an opportunity for us to use FTC1. So when I take the derivative of the integral, this goes in here. So I've got f of g of x times, careful, don't forget the derivative of that, g prime of x. So if I want w prime of 3, I want f of g of 3 times g prime of 3. G of 3 is 4, f of 4 is -1, g prime of 3 is 2, and I get -2. And I like -2 there. Okay, what about part D? Part D, G inverse is the inverse of function G. And we want to write the tangent line at x equals 2. Tangent to this graph, not tangent to G, tangent to G inverse. So this is the input on G, which means, I'm sorry, on G inverse, which means this is the output on G. When is the output equal to 2 on G? And that happens at 1. So I know that G of 1 equals 2, therefore G inverse of 2 equals 1. So I've got an ordered pair. I also need G prime at 1. So G prime at 1 is 5. And remember, the slopes on the inverse function at the inverse point is the reciprocal of the regular one. If you think of slope as a change in y over a change in x, and then you think about the slope where we switched the x's and y's, the slope on the inverse function is going to be a change in x's over a change in y's, and this is the reciprocal of that. So G inverse prime at 2 equals 1/5. So then I've got y minus 1 equals 1/5, x minus 2. Do I need to do anything besides write the equation of the tangent line? No, I did not. I'm all done with this packet. I hope that was helpful.